Hello friends, my name is Akshans and welcome to CADDD Academy. In this lecture we will be discussing about Biot-Savart's law. Okay, to understand the Biot-Savart law we need a scenario like, let's say we have a current carrying conductor which is carrying a current in upward direction like this, and this conductor has length of, let's say, dl. Okay, and as we know, if current is moving upward, then the magnetic fields line are like the fingers rotation. Okay, like the fingers rotation of our right hand. Okay, so this is the current carrying conductor and this is the magnetic field lines. Okay, this is magnetic field lines. Okay, so let's take a view of this thing from here. Let's say view, this thing will look like so. This will, okay, this cylinder will look like a rectangle and current moving upward, and these magnetic field lines, this is coming from here and here it's going inward. Okay, here upward and here inward, so this is upward and this is downward, let's say inward to the paper. Okay, so this is coming like here, it's coming upward and going downward, coming upward and making a circle around the conductor. Okay, so let's say this is a point where we have to measure the magnetic field density. Okay, so this point we will write as d of magnetic field density. Okay, so because this is dl, differential length, then the magnetic field density at this point will be differential magnetic field density. Okay, and we will integrate to get the whole magnetic field density. The distance between these points, okay, this is the center of the conductor and here this distance is r12. Okay, and this distance is a vector quantity, it has direction also. So here dB is proportional to, directly proportional to the amount of current. Okay, if current will be more, then the magnetic flux density will be more. Okay, with the length, which is differential length here. Okay, if length will be more, then the density of magnetic field will be more. Okay, and inversely proportional to square of the distance. Let's say this is the distance and okay, r12 is the distance from here to here, and square of the distance is the inversely proportional to the magnetic field density. So to remove the sign of the proportionality, we have to introduce a constant here, and that constant is mu by 4 pi. Okay, and the rest of the things as it is. Okay, where this mu is equal to mu naught into mu r. This mu r's value for air is 1. Okay, and the value of mu naught is 4 pi into 10 to the power minus 7 Henry per meter, and this thing has the direction which is r12 cap. Okay, so simplifying this equation further, and differential magnetic field density is equal to mu naught by 4 pi, because generally we consider it as in air, so we are writing just mu naught, and mu r's value is equal to 1. Okay, so I dot dl here r12's square, and this is r cap, r12 cap. We will write it as r12 as a field divided by the magnitude of r12. This is quite similar like Coulomb's law we have discussed in last classes. So after putting this thing here, we will have dB, differential magnetic field density, is equal to mu by 4 pi I dot dl r12's cube. Okay, this thing is getting multiplied here, and r12 as field, which will give the direction of this thing. Okay, so this is the Biot-Savart law, and all magnetic field studies is completely based on this Biot-Savart law. But as we know, the direction of line is here upward, and the direction at which we are calculating the magnetic field is this side. Okay, so these both are orthogonal, okay, 90 degree to each other. Okay, so we can't do the dot product here, so we have to do the cross product.